So this is part 1 of the chapter 5 review, which will be about wind. So first let's talk about how we measure the wind speed. So nowadays we use a special instrument called an aerovane, spelled A-E-R-O-V-A-N-E, an aerovane, which combines some other instruments. It combines a wind vane and an anemometer into a single instrument. So the wind vane measures direction and the anemometer measures the speed of the wind. They used to be two separate instruments, but now we figured out how to combine them onto a single convenient device. So this is what we use to track wind all around the world. Now a wind vane, you might see it at your grandparents' house. It's the fancy decorative thing with maybe a rooster at the top that will spin in every direction, and based on where the prevailing wind is, it'll point towards where it's coming from. That's how a wind vane works. Whereas an anemometer will spin around based on how fast the wind is moving. So a stronger wind will move that anemometer around very quickly, and it's able to give us pretty much instantaneous feedback on how the wind is behaving in a specific location. So if you ever watch a local weather report and it shows a diagram of current wind speeds, it's using an aerovane to give real-time feedback to the weather station, and that's what they're displaying on the map. Another way we measure the wind is with something called the Beaufort scale. And rather than using the exact wind speed, the Beaufort scale measures wind based on its effectiveness on an object. So a very light breeze might blow a piece of paper away. A very strong breeze from a hurricane might rip the roof off your house. That's an example of how the Beaufort scale works. So winds are named from the prevailing direction of which they originate. So winds tend to have one specific direction where the wind speed is much stronger than the other directions at a specific location. And we name the wind based on that. So a westerly wind originates from the west, and it tends to flow more eastward. An easterly wind comes from the east, a southerly wind comes from the south, and so on. So in almost every instance, we name the wind based on the prevailing direction where most of the wind speed comes from. That's the dominant direction. So the only exception to this general rule of naming a wind from the prevailing direction has to do with onshore and offshore breezes. So an onshore breeze refers to a breeze that comes from the sea and moves onshore onto the land. So it does not mean a breeze that started onshore and moved out to sea. An onshore breeze starts at sea and moves onto land, and the opposite is an offshore breeze. An offshore breeze starts on the land and moves offshore out to sea. That's the one exception to our general rule of how we name the winds. So wind is caused by differences in thermal pressure, which results from changes in temperature, and that causes winds to blow in a certain direction. So an area that has a uniform air density and a uniform air pressure will have no wind because there's no pressure force gradient that causes air to blow in a certain direction. Wind will only blow when there is a pressure force gradient between two spots that causes the air to want to balance itself out, and it does that. It balances that pressure out in the form of the movement of wind. So in very relative terms, warmer air is associated with lower pressure, and relatively cold air is associated with higher pressure. In very relative terms, there are obviously specific differences all around the earth, but in relative terms, warm air will have lower pressure and colder air will tend to have higher pressure. So there are three forces that control the wind speed and the direction near the Earth's surface. So we're talking just about surface winds, the winds that are high up in the atmosphere and the winds that are below the ocean current are a little different. We're talking just about surface winds here. The three forces that control these are, first and foremost, the pressure gradient force. That's the most important one. It's the one that primarily determines the wind speed and the direction, and air will always flow from areas of higher pressure to areas of lower pressure. Never the other way around. Always higher pressure to areas of lower pressure, because the air is trying to achieve equilibrium and balance that pressure out. So it has to move from an area of higher pressure to an area of lower pressure, because those air molecules, they want more space. They don't want to be packed in a high pressure area. They want to expand and move into an area of lower pressure and achieve a state of balance by doing that. So that's what the pressure gradient force does. The greater the difference in pressure between two regions, the faster the air will flow between them, the higher the wind speed as the air tries to achieve that pressure balance. An extreme example of this is a hurricane. A hurricane goes through an extremely quick pressure change over a relatively short distance, whereas a very slow wind, there isn't much of a pressure change at all. So there's not much of a need for the air to balance itself out. And again, an easy way to remember this, like I mentioned in the class, the pressure gradient force is just to think of opening a freezer. Your freezer is going to be much colder. The air inside will be much colder and more dense than the air outside of your freezer. So when you open your freezer door, that cold air is going to immediately rush out into the open air, because it's an area of very high pressure and it's trying to expand into an area of low pressure. That's an easy way to remember how the pressure gradient force works. It's always going to flow from an area of high pressure to low pressure, never the other way around. So we covered pressure gradient force. There's two others. Second, we have the Coriolis force. So the Coriolis force is caused by the rotation of the Earth. It takes 24 hours for the Earth to make a complete rotation, and that rotation also causes a difference in pressure, and also it tends to create wind. And this effect is much stronger at the poles than it is near the equator. Near the equator, it has a very minimal effect, and that makes sense, right? Because as the Earth spins around, it's spinning much faster at the poles than it is near the equator. Because everywhere on Earth it takes 24 hours to rotate, but the distance at the equator is much greater than it is at the poles. So it causes that Coriolis force to have much greater effect at the poles than it does at the equator. And for our purposes in the northern hemisphere, this Coriolis force will deflect objects to the right. In the northern hemisphere, it deflects objects to the right. In the southern hemisphere, it's the opposite. In our third force, we have the force of friction, which directly opposes the pressure gradient force, just like most things in the world of physics. If an object tries to move in one direction, the force of friction at the surface will try and stop that. So as air flows down a pressure gradient, the drag of friction will slow it down. It tends to not have a huge effect, but it does have an effect on the way that wind moves, in some places much greater than others. And it only exists within a certain limit of the atmosphere we call the boundary layer. It does not exist in the higher levels of the atmosphere, which is why things like the polar jet stream exist, because at that point there's no more friction. So an airplane flight can take full advantage of that and use the really strong wind to save on jet fuel costs. The boundary layer only exists within about 1 kilometer of the surface of the Earth. So it's a relatively small area compared to the overall size of our atmosphere. So the instrument that we use to measure air pressure in the atmosphere is called a barometer, spelled Barometer, barometer. It's the instrument we use to measure air pressure. And in terms of the unit, we express air pressure in the unit called the millibar, as I said in Chapter 4, and millibar is abbreviated with a lowercase mb. Now, in normal atmospheric conditions, it tends to be just above 1,000 millibars, but sometimes it'll get into the 900s. On a really crazy high pressure system, it might get above 1050 or higher. So millibars is the unit that we use to measure air pressure, not to be confused with isobars. So isobars, on a map where we're drawing the air pressure zones, an isobar is a line that connects points of equal pressure. So let's imagine that the isobar says 1020 millibars. So at every point where that 1020 millibar line is, the air pressure at those locations is exactly 1020 millibars. And there will be other millibars that are either greater than or less than 1020 for us to compare to. And based on the direction of those isobars, we can determine the direction the wind is probably going. So the closer together the isobars are on a map, the greater the wind speed, because the pressure gradient is greater. Whereas if isobars are further away relatively on the map, there isn't as great of a pressure difference, so the wind speed is not going to be as great. The most extreme example would definitely be a cyclonic system like a hurricane. The isobars are going to be very tightly packed around the eye because it goes through a very quick pressure change in a very, very small area around the eye as the hurricane spins around. So if you see a sort of funnel shape on your isobar map, that's probably a strong indication that a cyclonic system is forming there. And the direction of the pressure gradient will always run perpendicular to the isobar, so it's always going to cross them at a 90-degree angle. It does not run in the same direction as the isobar lines, right? That wouldn't make sense because the isobars depict the change in temperature, so the change has to happen across those lines at a 90-degree angle. And I'll see if I can find a YouTube video to post for you guys that hopefully explains that better than I can with words. But on your isobar map, the prevailing wind direction will always run across the isobar lines at a 90-degree angle, not in the same direction as the isobars. So to wrap up part 1 of chapter 5, we're going to talk about the cyclones and anticyclones. So a cyclone happens when air flows towards a low pressure region and it creates a counterclockwise rotation in the northern hemisphere. In the southern hemisphere, it's the opposite. But in our class, we're just worried about the northern hemisphere. And in our part of the world, a cyclonic system will have a counterclockwise rotation. The most famous example would be a hurricane. So in other parts of the world, hurricanes are called other things like typhoons. In Asia and Australia, they're just called cyclones. But we use the Spanish origin term of hurricane. It's just a name for a cyclonic system. And in our part of the world, they flow counterclockwise. Now, the opposite of that is an anticyclone. Anticyclones form around areas of high pressure, and they flow clockwise as the air is trying to escape that area of very high pressure. It funnels out in every direction in a clockwise fashion. So cyclones turn counterclockwise in the northern hemisphere, while anticyclones flow clockwise. So cyclonic storms like hurricanes can be very destructive, whereas anticyclonic storms tend to not be very destructive, but they do have a tremendous impact upon how much rain certain locations receive. So to use our country as an example, the East Coast is far wetter than the West Coast because of the influence of some anticyclones. Out in the Pacific Ocean, there's an anticyclone that pushes humid air away from the West Coast. Only the northwestern part of our country really gets that moist air. By the time it gets down to California, it doesn't have very much precipitation left because of the presence of that anticyclonic system. So that's why most of California and the southwestern United States is a desert, because the presence of that cyclonic system is blocking moist air from reaching areas where it would otherwise go. And the opposite happens on the East Coast. So we also have an anticyclone that sits out in the middle Atlantic Ocean and pushes a lot of warm, wet air into the east and southeastern part of our country. So during the summer, that's why the southeastern part of our country gets so much rain. I'm not so much talking about the Gulf Coast where we are, but the East Coast, like DC, Philly, Atlanta, Florida, that's why they get a lot of rain, because that anticyclone pushes it there. That wraps up part 1 of our Chapter 5 review. In part 2, I'm going to talk about the global pressure belts.